Hello. We have completed discussing about RSA crypto system, which is based on the problem of factorizing numbers. That means given a number, we believe that it is difficult to factorize that number into its prime factors. Today we are going to discuss about another way of constructing public key crypto systems, which is based on discrete logarithm problem rather than the factorization problem. This is discrete logarithm problem. So in this branch of ciphers, we use the hardness of we assume the discrete logarithm problem, the solving discrete logs is hard, and based on that we develop the crypto systems, we construct the crypto systems, and we prove the security based on the hardness assumption of discrete logarithms. So discrete logarithm ciphers are currently the main public key alternative to RSA, or that the crypto systems we used based on the hardness of a factorization problem. So they are widely deployed and standardized. When implemented on elliptic curves, they can be more efficient and compact than RSA. So in this course, we are not going to discuss about elliptic curve crypto systems. Elliptic curve crypto systems are like elliptic curves are kind of curves we can find in mathematics. That curve is generated using elliptic curve functions. So in elliptic curve ciphers, in our normal other ciphers like RSA or discrete logarithm ciphers, we use the real numbers, not the real numbers, the integers as the set of numbers as the pool for the computation. But in elliptic curve ciphers, instead of that real numbers, we use the points we get from the elliptic curve. So when we we draw the elliptic curve, we can find the points where we use them as the pool or set of elements to compute our cryptographic operations. So we are not going to discuss about that anymore. It is said that when we implement this discrete logarithm things using the elliptic curves, so using the points we get in elliptic curves, it is more compact than RSA. So that means in RSA we have to use, to obtain the security, we have to use numbers with 1024 bits. So that sort of big numbers. But when we have elliptic curves, we can use shorter numbers, shorter numbers depending on the elliptic curve points, and because of that, computation is a little bit more efficient. So in the context of integers or the real numbers, we find that so we take the numbers from zp is the integers modulo p. Z is the we define we use Z to define the set of integers under modulo p. So this is the set of elements we used for our cryptographic operations for the computations, not the elliptic curves at this point. So recall that Zp is the set of non-zero integers modulo p. In this lecture, p will always be a prime number, so large prime number. So all the numbers less than this large prime number are going to be the integers modulo p. So for example, if we take p as 17, 17 is not a large prime number, but for example, I would say if we choose 17 as the prime number, then all the numbers less than 17 are going to be like relatively prime to the number 17. So all the numbers there. So likewise, we use p, we get p as a we get a large prime number p, and all the numbers less than that will be in this set Zp. So the order of an element g in modulo arithmetic is the smallest integer r such that gr mod p equals 1. So the order of an element g in modulo arithmetic is the smallest integer r such that g to the power r mod p minus 1, and this g value is called the generator of this group. So we know that Fermat's theorem, so I think you have followed the supplementary slides I have provided at the beginning of this lecture series. So you may have seen this Fermat theorem, and according to Fermat theorem, all elements have order at most p minus 1. So in fact, a general theorem of algebraic groups implies that the order of any element must exactly divide p minus 1. That's according to the group theory. A generation of Zp is an element of order p minus 1. So here we have the Fermat's theorem, bottom of the slide. You can see it. And these are the theoretical background we have to have in mind to continue this topic. So finding a generator of Zp. So generators exist for Zp for all primes p. In fact, there are 5 p minus 1 of them. This is the number of generators we can find in a group Zp. So Zp star means that this is a multiplicative group. So all the elements of this group is generated by multiplying operation. To find generator, we can choose a value g and test it as follows. Compute all the distinct prime factors of p minus 1 and call them f1, f2, f3 until fr. Then g is a generator as long as g to the power p minus 1 divided by f I not equals 1 mod p for I equals 1, 2, 3 up to r. So you have to leisurely follow this mathematical background and understand that to really understand this topic. Since our time is very limited, I'm not going to go very deep into the mathematics here. My intention is to give you the basic idea about the applications and usage of these the ciphers and what are the ciphers available for us. Okay, now this is a small example with numbers. You can follow that, and let's look at discrete logarithm problem, which is the core part of this kind of ciphers. So let G be a generator of a group, multiplicative group is at P for a prime P. The discrete logarithm problem over this group is given Y in ZP. So Y is an element of this ZP group, ZP star group. So that Y is an element of this multiplicative group. Given Y, find X with such that Y equals G to the power X mod P. So you are given y, you are asked to find a value x such that generate a g to the power x mod p equals y. So this is the discrete logarithm problem. So we can easily compute the exponentiation. We can compute the exponentiation like given x, we can compute g to the power x and get the y. But given y, it is difficult to find x such that g to the power x gonna be y. So that's the discrete logarithm problem. We believe this is computationally hard, or exponential time algorithms are there to solve this, not polynomial time algorithms. So this is the available solution for this kind of problem is difficult to compute within our computational limit. So if p is large enough, this is believed to be a hard problem. So this is the core or the base of discrete logarithm ciphers. So we believe that this is hard, and based on that, based on this discrete logarithm problem, we build up the ciphers. So the best known algorithm for finding discrete logarithm in set P is a variant of number field sieve, uh, and we know that number field sieve is sub exponential time problem. So this is not very efficient. So recall that number field sieve is sub exponential time algorithm. So because of that, solving discrete logarithm is believed to be hard, and whatever crypto system based on discrete logarithm can be at least hard as solving discrete logarithm. Okay, this is an example about how to compute the elements in a group. So in this integers mod 19 is used, z star 19. So all the elements less than 19 are relatively prime to 19. So there are 19 elements, 18 elements there in this group. So generator is g, and when y equals g to the power x mod p, then log p of y equals x. For example, log 2 of 3 is 13. So you can see that g to the power 3 is going to be 13. Likewise. So based on this discrete logarithm problem, one of the famous building block for cryptography is built, which is Diffie-Hellman primitive. We call it Diffie-Hellman Key Exchange because it is used as the base for key exchange protocols very widely. So I think you have sometimes heard about this Diffie-Hellman protocol or this kind of key exchange protocols, this thing. So designed to allow two users, Alice and Bob, to share a secret using only public communications. So we have public communication channels. What we do is we exchange values in that channel in a way that it is difficult for the third party who is observing at this channel to compute the secret value shared using this public channel. So values shared in the public channel are some computation of a secret value, but it is difficult for the third party to uh, extract the secret from that. Okay, so the public knowledge here, the both parties and the third parties and everybody knows the large prime number p, the generator g of this group ZP. By having P, anybody can compute the all the elements of this group G. So group ZP. That's the element that all the numbers less than P are going to be the elements of this ZP multiplicative group. And generator is G, which is public parameter again. And Alice and Bob each select a random values A and B respectively uh, in a way that A and B are between 0 and P minus 1. And then Alice sends G to the power N G to the power A mod P to Bob over insecure public channel, and Bob, who selects B value, computes G to the power B mod P to Alice over this insecure channel. Once both of them got the message coming from the other one, then they compute G to the power AB mod P. So what Alice does is Alice receives G to the power B mod P. Alice doesn't know the value of B, but she knows the value of G to the power B, not B. And she computes G to the power B to the power A, because Alice knows A value. Bob knows B value, but Bob doesn't know the Bob doesn't know the A value. Instead, he knows that G to the power A value. So Bob can compute G to the power G to the power A, that is the value he gets from Alice, to the power B. So finally, both of them compute G to the power AB mod P. So in the next slide, we have the diagram. You can understand it easily. Alice chooses A and computes G to the power A mod P and sends to Bob. Bob chooses B. Bob sends G to the power B mod P. Once Alice gets this G to the power B mod P, Alice can compute that value to the power A. Bob can compute using the value he gets from Alice to the power B mod P. Alice doesn't know the B value, Bob doesn't know the A value. Alice only knows A, Bob only knows B. But we can see, finally, both of them compute the same value. So according to the hardness of discrete logarithm problem, this is the discrete logarithm problem. So we give a value from the which is a group element, but we doesn't give value A such that G to the power A equals something. So for example, you can see this is like here, I will draw that. So let's say this is value A, capital A, and this is value capital B. Alice computes a capital A value by computing G to the power A mod P. The public people, the people who are looking at the channel, who can tap the channel or do whatever, they see this value A, capital A. But using A, getting the simple A value is same as solving the discrete logarithm problem. Given this value, computing a value A such that G to the power A equals capital A is the discrete logarithm problem. This is called discrete logarithm problem. If this is hard, if discrete logarithm problem is hard, this protocol can be considered secure because this is based on discrete logarithm. So here is a simple example with numbers. We can try that and verify the correctness of this Diffie-Hellman computation. And also, I think you can understand this protocol is secure because nobody can compute the Z values without knowing A or B individually. To get A or B, the third party should be able to extract the simple A or simple B using the capital A or capital B value that he sees from the public channel. So this is the security of Diffie-Hellman protocol. An attacker who find the discrete logarithm can break the protocol. So intercept the value g to the power a mod p, which is I used capital A, and take the discrete log to obtain a, and then compute g to the power ab because he can see the capital B value in the public channel. But anyway, the person who is going to break this protocol at least should be able to solve the discrete logarithm problem and get simple A or simple B value from that. So there is no better way known for a passive adversary. Passive adversary means the attacker is not involving in the protocol, not involving the computations in the protocol. Attacker is just observing passively. Passive adversary means passively observing, just observe the communication happens and try to extract the values from that. Active adversary means the opposite of this passive adversary. Active adversary is the person who is actually providing values for the communication. For example, in this case, if the adversary is active, adversary can be a person who choose value simple A or simple B and force the Alice or Bob to use that value in the protocol. So active adversary is inside the operation. He is inside, not just observing and trying to extract values from that. Instead, he is actively providing values or the parameters for the protocol computation. So far, better way for attacking this protocol is unknown. So therefore, we believe to break this protocol, we have to solve the discrete logarithm problem. If discrete logarithm problem is hard, we say this protocol is hard to break. Similar to the concept we used in RSA crypto system. There we said the only known way to break the RSA is to solve the RSA problem or break the RSA protocol is to solve the factorization problem. So similar concept is used here as well. Then we should talk about this authenticated Diffie-Hellman. Here you can see there is no authentication in Diffie-Hellman protocol. Alice choose A, the simple A, and compute the capital A value. Bob choose simple B and compute the capital B value, and they exchange two values. But once Bob gets the capital A value from Alice, Bob has no evidence or guarantee that this capital A value is really coming from Alice. So there is no authentication. Still, this protocol is theoretically secure, not possible to break it. That means not possible to compute the Z value, but there's no authentication. To avoid that, we have to provide authentication into this protocol. So in the basic Diffie-Hellman protocol, the message between Alice and Bob are not authenticated. Nobody is providing any guarantee or proof saying that this value is exactly coming from him. So it is obvious that a networking situation, neither Alice nor Bob knows who the secret Z is shared with unless message is authenticated. So anybody can say, I'm Alice, I'm sending this to you. Bob doesn't have any mechanism to verify whether this is coming exactly from Alice or somebody else. So, so various more complex protocols exist. For example, adding digital signatures is one alternative to provide this thing. In this, the picture in the bottom of the slide, you can see how the digital signatures are used to authenticate the messages. So after this communication, three-way communication, finally, Alice and Bob both can get signs values from the other one. So by checking the signature, verifying that signature, both of them can come up with a guarantee that this message is exactly coming from Alice and this message is exactly coming from Bob. So that's authenticated Diffie-Hellman using digital signatures. Another way is using static and ephemeral keys. So what are static and ephemeral keys? In our previous plain Diffie-Hellman protocol we discussed, here we see Alice chooses a simple A value, Bob chooses simple B value, and then Alice computes capital A, Bob computes capital B. So in this example, these simple A and simple B values are used only for this communication session. So they are temporary or short-term keys only for this communication session. So they are called ephemeral keys. But if we have something long-term, let's say like Alice chooses a value simple A and keep it with him or her for a long term, and Alice publish a capital A value computed using this simple A and say this is my public key. So for example, I can say like Alice chooses a simple A value which is the static secret key of Alice and compute the capital A value and then register the value A at some trusted third party, let's say like some registration, and then through that registration Alice publish that value in a telephone directory or something. So capital A value is coming from Alice, which fact is registered and published through a trusted third party. So Alice can use that trust from the trusted third party, that registration, and use the simple A value as the long-term secret key of Alice. And capital A value will be the long-term public key of Alice. So in this way, we can see that there is a trust for the value capital A because of the trusted third party we use. So this is called using static keys for authenticated Diffie-Hellman for authentication. And to make, so in that case you can see that all the time secret key is going to be the same, not the secret key, the shared secret between Alice and Bob is going to be the same because Alice registered his public key in the trusted third party and Bob registered his public key in the trusted third party, and all the time the key used by the shared secret between Alice and Bob, the value Z, is going to be the same. So in a situation that somebody can steal the simple B value from Bob, from that point onward can interrupt any communication happening between any party with Bob, because he knows the value B and he knows the public value from the telephone directory, like the directory registration, and using that he can compute any shared secret between any party with Bob. So this is problematic. Because of that, we cannot satisfy with static keys, only with static keys for authenticated Diffie-Hellman or authenticated key exchange. We have to add freshness for sessions. To add freshness, we use ephemeral keys. Ephemeral key is a key, a secret key and a public key pair, which is used only for that particular session. So if there's a session between Alice and Bob, they use their static public and secret keys, as well as they choose a ephemeral key or one-time key for that specific session only. And combining both the keys, we can have authentication and also the freshness of the session. So even though somebody steals the simple B value from Bob, he cannot get the shared secret values with anybody with Bob, because there is a freshness for each shared secret. So we have to use static and ephemeral keys to provide better security and authentication for key exchange protocols. So usually in cryptography, we don't use signatures to authenticate, because having a signature scheme inside the key exchange part or the Diffie-Hellman protocol is kind of heavy computation, signature and Diffie-Hellman. Instead, we use static and ephemeral keys and add the authentication as well as the freshness to achieve better security. Okay, I think you can understand it if you follow the lecture and the slides and draw in a paper very carefully and patiently. But these things are like, you have to spend some time and try to understand very clearly and leisurely. Okay, so Diffie-Hellman kind of thing, it is based on discrete logarithm problem, but Diffie-Hellman is not only used for that kind of key exchange or sharing a value. Not only for that, that concept can be used for create encryption schemes like RSA. Not RSA, but some public key encryption scheme in other way rather than RSA computation. So one more like one prominent and well-known encryption scheme is Elgamal encryption scheme. This is proposed by Tahir Elgamal. He is in 1985. He is Egyptian cryptographer or mathematician. So he turns the Diffie-Hellman protocol into a crypto system encryption scheme. So we can look at this encryption scheme in this lecture, but I don't want to go very deep into the computations of Elgamal encryption scheme, but we can just have a slight look at that. So this explains how the encryption key generation happens. So select a prime P and generate a G of prime order multiplicative group P, and select a long-term private key X from that prime order group and compute Y in a way that G to the power X equal mod P equals Y. So the public key in this encryption scheme is P, the G, the generator, P is the order of the group, and Y value. So this is how the encryption and decryption happens. So this public key is publicly known to anybody. and the person who is going to encrypt a message for using this public key do like this. He computes, he has a message is it itself, we can convert any message into a number, because anything is numerical in computation. And there's a message M which is between 0 and P. Then randomly choose K value and compute G to the power K mod P. And the message, the ciphertext is G to the power K mod P value and M times Y. Y is the public key of this parameter of this public key, Y to the power K mod P. So these two values are the ciphertext. Once this is received by the receiver, or the person who has the X value, he can say, so the C1 is G to the power K mod P, C2 is M times Y to the power K mod P. He can compute C1 to the power X, because X is the secret value. It is only with the receiver. C1 to the power X mod P, and then, so this slide is not clear for me, just give me a few seconds. And compute C2 times C1 to the power X inverse mod P. So that will be the plain message, the decryption. So this is how this Elgamal encryption works, which is based on discrete logarithm problem. And why it works: the sender knows the ephemeral private key K, which is the random value he chooses. The receiver knows the static private key X, which is the long-term key. I told that this kind of static keys are used to provide authentication, and because of that, he can use the public key, public value published in the directory for the encryption purpose. The both sender and the recipient, the sender can choose the public value corresponds to the long-term private key or the secret key X, and do the encryption. And both sender and recipient can compute Diffie-Hellman value for the two public keys, C1 G to the power K mod P and Y G to the power X mod P. The Diffie-Hellman value Y to the power K mod P is the C1 to the power X, and this is used to mask or the hide the message M. So he has just to compute it and take the inverse for the decryption, the receiver. So this is a simple example of how the Elgamal works using the numbers. You can follow that easily. And security of Elgamal encryption scheme. So if an attacker can solve the discrete logarithm problem, the system can be broken by finding the private key X from G to the power X. It is quite possible for many users to share the same P and G values. Okay, same P and G means the P is the prime order value and G is the generator of that prime group. There is no need any padding as in RSA. Notice that each ciphertext is already randomized because the K value is chosen at random. Because of that, ciphertext is randomized. The Elgamal crypto system has a proof of security in a good model, subject to the Diffie-Hellman, subject to the difficulty of the so-called Diffie-Hellman problem. Diffie-Hellman problem is based on the discrete logarithm problem. So Diffie-Hellman problem, I will just explain the Diffie-Hellman problem. I will draw here. Diffie-Hellman problem is once the generator G and the P value is known, these two values are known, we randomly choose value A and value B and compute capital A, that is going to be G to the power A, and capital B, that is going to be G to the power B, and the challenge is we give the challenge like this. We give the value A and B, but not simple A and simple B, and G and P values are also public. We give this thing as well, and then ask the person who is facing to the challenge to compute G to the power AB. This is called Diffie-Hellman problem. So anybody who can solve the discrete logarithm problem can easily solve Diffie-Hellman problem. So if the Diffie-Hellman problem is hard, obviously we can say like if the discrete logarithm problem is hard, this is the only known solving the discrete logarithm is the only known way to solve Diffie-Hellman problem, and Diffie-Hellman problem is going to be hard. So we say that the Elgamal encryption scheme is based on Diffie-Hellman problem, that is what I explained here, and because Diffie-Hellman problem is hard, Elgamal encryption scheme is secure. Okay, so I'm not going to discuss about elliptic curves here, but there are some information, you can follow that, and if you like you can find read, and this is some comparing the strength of elliptic curve cryptography. The main thing here you can see is in the symmetric key length of 80 bits is equal to RSA modulus length 1024 for public key cryptography. Symmetric key cryptography is computationally like not very expensive. That's why it is used for mass communications, data communications. But RSA cryptography, or this RSA cryptography, it is a public key encryption. Public key encryption is very much useful to share secret values using public channels which are not secure. So once the secret values are shared, secret keys can be generated, and from that point onward, those secret keys can be used for the symmetric key encryption schemes. If it is RSA, 1024 bits, which is equal to elliptic curves with this length. So that's why we can say elliptic curves, once implemented in elliptic curve groups rather than prime order groups, we have to deal with numbers which are smaller size. So it is going to be compact and efficient. So this is about elliptic curve cryptography. The most crypto systems based on discrete logarithms, that means using the prime order groups ZP, can be implemented using elliptic curve groups. So Diffie-Hellman Key Exchange, Elgamal can be easily implemented using elliptic curves. What we discussed here is using the prime order groups, but they can be used in elliptic curve groups as well. So elliptic curve cryptography is widely deployed today, and the Canadian company called Certicom holds many patents on some mathematical ideas about this elliptic curve cryptography. So most of the crypto systems that are initially proposed in prime order groups can be used in elliptic curve groups as well. It is more compact and more efficient. Okay. Now if you see this kind of thing, like when you check the certificate and connection of your websites, you can find this kind of information. The connection is encrypted, authenticated using AES 128 and uses ECDHE, ECDSA as key exchange mechanism. What does it mean? It says this connection is used to communicate and that are encrypted using AES 128-bit mode, and also it uses elliptic curve Diffie-Hellman using ephemerals and elliptic curve digital signature scheme for key exchange. And here also the connection is AES 128, elliptic curve Diffie-Hellman ephemeral, and RSA as the key exchange mechanism. So now you can have some kind of evidence that all the crypto systems, the theoretical boring things we discussed here, are actually in use in your day-to-day communications. Your websites, your mobile phone apps, credit card transactions, emails, and whatever the things you do, the sensitive things you do through internet are going to be secured with these kind of mathematical building blocks. So in our university, I checked this few years ago, and our website was it used TLS 1.0 version at that time. I'm not sure what it is using at this moment, and the connection is encrypted using AES 256 CBC. CBC means cipher block chaining mode, and with hashMAC and SHA-1 for message authentication, and RSA as the key exchange mechanism. Okay, so these are the stuff I wanted to discuss, and I try to minimize the mathematical and theoretical stuff as much as possible. Lectures can be a little bit or completely boring because if you don't have that kind of interest in mathematics and cryptography, but at least try to get basic understanding, because as computer engineers you have to have some kind of understanding about cryptographic primitives. It is important. Okay, thank you very much.